So this is the oscillating plate and this is the sand particle, and they are doing SHM. We know that for SHM, the acceleration is always proportional to the displacements from the equilibrium position, but directed in opposite direction to the displacement. So this is the equilibrium position. So when it's at the equilibrium position, the acceleration is 0. At any positions above the equilibrium position, we know the acceleration has got to be directed downward. On the other hand, at all positions below the equilibrium position, the acceleration has got to be upward. So what are the forces that are acting on the sand particle? There's of course the downward weight, and this downward weight is constant regardless of the position of the oscillation is at. The only other force acting on the sand particle is the normal contact force that the plate exerts on the sand particle. When it's at the equilibrium position, the contact force must be exactly equal in magnitude to the downward weight. Because at the equilibrium position, the acceleration is 0, so net force must be 0. So these two must be equal but opposite. At any position above the equilibrium position, what is required is a downward acceleration and therefore a downward net force. So we know that the normal contact force will be smaller than the weight at any position above the equilibrium position. So the opposite is true at all positions below the equilibrium positions. What is required is upward acceleration and upward net force. So the normal contact force should be larger than the weight at positions below the equilibrium position. So we know the plate is motorized to do is whatever SHM it is doing. As for the sand particle, the normal contact force and the weight must combine to produce the correct net force and acceleration so that it does the exact SHM as the plate does. There's no problem with the sand keeping up with the plate at any position below the equilibrium position, because below the equilibrium position, what is required is an upward acceleration and net force. So what's required is the normal contact force to overcome the downward weight to provide the required net force, and there's no limit to how large this normal contact force can be. As long as the molecular structure of the plate holds, it can provide whatever amount of upward normal contact force that's required to keep the sand doing the same SHM as the plate. The problem comes about when the oscillation is above the equilibrium position, because what is required is a downward acceleration and net force. So we need the weight to overcome the normal contact force to provide the required downward net force. But the downward the force that's providing the downward force is the weight, which is fixed in magnitude. In fact, we have to rely on the normal contact force to weaken if we want to have a large downward net force. So there's a maximum to how much downward net force we can have. The maximum is actually mg. That happens when the normal contact force is 0. Okay, let me write out an equation that will summarize all that I've said so far. So, taking downward to be positive, so the downward weight minus the upward normal contact force is equals to my mass times my acceleration. I'm talking about the sand particle, of course. And of course, I know acceleration is omega square x, so I can write it as this. So you see, as we increase the amplitude, we'll force the oscillation into larger and larger displacement from the equilibrium position. This will require a larger and larger downward net force, which will mean that the normal contact force will become weaker and weaker. But if the amplitude is so large, that the normal contact force has become 0, then we have reached the limit of maximum downward force we can get. And when that happens, mg is equal to m times a, right? And therefore this happens when the acceleration is g, downward. Many students like to ask whether the sand loses contact when the plate is on the way up or when the plate is on the way down. Actually, it can be either, but it can only happen above the equilibrium position. So if it happens on the way up, it's because on the way up, the plate decelerates faster than the sand. So on the way up, the plate decelerates faster than the sand, and that's why the sand sort of like floats above the plate. It loses contact. It can also happen when it's on the way down. That means the plate is accelerating towards the equilibrium position at a rate faster than the sand. And again, the sand will sort of like float above the plate and it loses contact. Either way, it loses contact because the sand cannot keep up with the downward acceleration of the plate. And this is because there's a maximum downward acceleration for the sand particle. The maximum downward net force it can experience is mg, and therefore the maximum downward acceleration for the sand particle is g. If the plate has a downward acceleration that's larger than g, the sand particle cannot keep up with its SHM. Okay, I hope I've made it clear. That's all. Ta-ta!